All right. So as you were saying, let's quickly move to solve our question. Quick. That is, we are going to continue from A. Okay. So we are coming to our solution now. And this is our solution. Solution. So this is our solution. This is our solution. So first of all, we even want to start by solving the A. Stresses in each section. Okay. But why don't we just take one section and then after we are done paying for one section, we also come and focus on the other. Okay. So we are actually doing for stresses in each section. Let me put it over here. Stresses in each section. So that is the stresses in each section. In each section. Stresses in each section. So from here, let's just pick section one. Let's pick section one. So let's pick section one. Let's pick section one. So I want us to focus on just section one. This is the section one. Okay. So we can draw section one even over here if you like and use it to solve our problem. You see. Uh-huh. So for section one, if you say we should calculate for the stress in section one, it's not a problem because we know section one and we know the details that section one says. Look at the section one over here. What is section one having that is making it so special? It just have a length of 200 mm and a diameter of 20 millimeters. Okay, so we can just pick section one and even let's choose to draw section one here now and use section one to solve our work. Okay, it is as simple as that. Since the bar is in tension, we still maintain it over here as you are seeing. You see, so this becomes the 35 kilonewton. 35 kilonewton. 35 kilonewton. Let me write also over here 35 kilonewton. So from here, how do we write? This becomes 200 millimeters. 200 millimeters. Okay. So this is it. This is it. This is it. 200 millimeters. And inside here, we know that, let's also go and verify again. We know that it is 2 centimeters, okay? Which later then became 20. Okay, so let's write 20 millimeters inside and let's use it to solve our work. You don't have to be in a hurry at all. You have to take time, okay? And make sure that you are doing the right thing. Quality is better than quantity. Okay, if you rush and you say you are done, quick, you are gone. Meanwhile, there are mistakes in the work. It doesn't speak well of you. Okay, so after you are done drawing, putting the diagram here, we are in the solution. Oh. Then you come and do what? Put down your formula. But you say you should calculate for stresses in each section. What is the formula for your stress? You know that stress is equal to what? Force over area. Okay, so first of all, you know that stress is equal to force over area. Force over area. Force over area. Okay. So once you're able to put your formula down, then it means that you can also write it in terms of the symbol. So this is P. Okay. And then this is what? Area, which is what? A. Without talking much, you realize that the area is measured in Newton. Okay. So if I write this thing over here, don't get confused. The area is the load is measured in Newton, and then the area is measured in what? Millimeter what squared. In this our case. Okay. Exactly. So if I want to calculate for my stress, even without talking much, then it means that I can just by substitution, I'm just gone. Okay. So this is my stress now. I can say that my stress finally is equal to what? By substitution, I'll just put the formulas in. So the load over here is 35 kilonewtons. So I'm going to write 35,000. So this is 35,000. 35. 1, 2, 3. Okay. Newton. All over what? The area. But you realize that the area is what? Unknown in this case. So it means that we have to calculate for the area before we can put the area in it. You see? Uh-huh. So if that is the case, then let's find for our area. We can draw a very small bar over here and calculate for our area in it, if you agree with me. So we can calculate for the area in this small box I'm coming to do over here. Let's calculate for the area inside this one over here. What is the formula for the area we know? We know that the area is equal to what? Pi d squared over 4. Not just any d, it is the original, the outer diameter. So we write the as capital D. So pi d squared over 4. Okay. That is at the end of the day, this is going to give us, so the pi we are adopting in this case is what? 3.142. Okay. Times the diameter. The diameter was 20. Okay, so let's take the 20. So this is 20. Then I square it. All squared. Okay, all over what? 4. Okay. So finally, I can say that my area is equal to what? Somebody please tell me the formula for the area, the answer for the area. Let's all punch it together. Let's all punch it together. 3.142 times 20 all squared over 4. You realize that you're going to get 314.2 millimeter squared, and that is 314.2 millimeter squared. Okay, let me quickly check the comment section. Yes, Patricia also had the answer. That is Patricia AC. She had 314.2 millimeter squared. Yes, and that is the answer. So at the end of the day, now we know our area, so we can just substitute our area into the question, and then we are good to go. Okay. So as we were solving initially, our area, we know that our area is equal to what? 314.2 millimeters. Okay, squared. So we can just punch quick, quick, quick. We get our answer. We are good to go. So now I'm sure we all know the answer for our stress. So finally, we realize that therefore our stress at section 1. Okay, if I put this, don't get it means stress at section 1. So our stress at section 1 is equal to, so everyone, let's all do it together. Let's all do it together. That is what? 35,000. Okay, 35,000 over 314.2. And you realize that you are going to get 111.3940. Okay, that is Newton per millimeter squared. Newton per millimeter squared. So we are done. We are done for the first one. We are done calculating for the stress 1. We are done calculating for stress 1. Okay. That is the stress at section 1. Let's also go and calculate for the stress at section 2. Okay. Let's also come and calculate for stress in this section, the section 2. So it has a diameter of 30 millimeters and also a length of 250. You see, these are the lengths. Don't get confused. These are the lengths. This is what? Length 1. This is length 2. And this is the what? Length 3. Don't get confused at all. So let's just come and solve for our section 2. Stress at section 2. Because if you go back to the question, the question says stresses in each section, or each section means do it for everybody. So as we are done for the first one, we come and do for the section 2 too. So let's do for stress in section 2. That is what? Section 2. So right over here, section 2. So this is section 2. You see. Then from here, what do we do next? We can just put down a diagram. Okay. And the diagram was given as this, as you are seeing. The diagram is given as this, as you are seeing. Here was 30 millimeters. 30 millimeters. So as we are all seeing, that is it. 30 millimeters, you see. And then here is 250. 250 millimeters. 250 millimeters. You see. So uh quickly. This is in tension. This is in tension. This is in tension, as you are seeing. 35 kilonewton. So I'm going to write here 35,000. They are all in tension. 35,000 Newton. So we are going to do same thing for all. So that is 35,000 Newton. 35,000 Newton. You see. So from here, what do? We can now calculate for the stress and we are good to go. We already know the formula for the stress. So what can we do? We can just, and we are good to go. So we already know. So this is the stress 2. Okay, so I write here, this is stress in section 2. This is stress in section 2. And we already know that our stress is equal to what? Load over what? Area. Okay. But in this case, our area is unknown. So why don't we calculate for the area in this case? Why don't we calculate for the area in this case? So, which means that, but what? Our area. But what? Our area. But A is equal to 3.142. That is, but A is equal to pi d squared over 4. Pi d squared over 4. Okay. So if you do your substitution, what are you going to get? When you do your substitution, what are you going to get? Let's all quickly do that together. So we are saying that what? But A is equal to this. Okay. That is, if we do our substitution and we put the formulas into it, you realize that we are going to get what? 3.142. 3.142 times 30. Okay. So this is 30 all squared all over the 4. So finally, what are you going to get? You can say that therefore your area A is equal to what? Everybody, let's quickly do that together. That is what? 3.142, 3.142 times 30 all squared over 4. And finally, you are going to get 706.95. That is 706.95. 706.95. 706.95 millimeter squared. 706.95 millimeter squared. Okay, so from here, now since we know the area, we can just wrap up with our question and we are good to go. So now we know that our stress 2, we know that we know the hot, we know the force, we already know the area. So we know the area to be hot 706.95, 706.95. Okay, then over here we come and put over here what? 35,000. Okay, that is 35, comma 1. We bring 3 zeros. This is in Newton, and the denominator is in millimeter squared. You see? So it's just a matter of computation. Quickly punch this in your calculator. That is 35,000 over 706.95. And what are you going to get? 35,000 over 706.95. I can see some people punching in the comment section. Daniel had an answer. That is, he had 49.508. 508. Okay, that is correct. I want to maintain 4 decimal places. So I'm going to write what? Therefore, I'm going to conclude my stress 2. Okay, well, I can even put the answer over here. And that is my stress 2 became what? 49. You see, so the stress in section 2, we are getting 49.508. 508. Let's say 5. Okay. Let's say 5 Newton per millimeter squared. Newton per millimeter squared. Better still, if I don't want to bring this sign over here, then it means that I can just maintain it like this. Exponent negative 2. Don't get confused. The laws of physics are the same for all observers in uniform motion relative to one another. Okay, so we are done calculating for stress in section 1. We are also done calculating for the stress in section 2. Let's see how best we can become history after calculating for the stress in the section 3 also. Okay, so let's pick section 3 and let's make more history. Okay, so I'm going to pick section 3 quickly from here now. Let's pick section 3. So we are picking section 3 here. So this is our section 3. This is our section 3. Exactly. Exactly. So let's draw the our question first. Okay, let's draw the problem. Let's draw the problem. Look, over here you can see how the section 3 looks like. Okay, it has a diameter of 50. Okay, and a length of 220 millimeters. So that is how we are going to draw it to be like. That is how we are going to draw it to be like. So let's proceed. Since they are all in tension, we maintain the same for all. So here 35,000, 35,000 Newton. Here it also became our 35,000 Newton. For space purpose, if I write 35 kilonewton, don't get mad at me. It is all the same thing. Okay. And here, you see over here, now we are focusing on this last one. So here is 220, here become 50. You see. So here was 50, and then here became the 220. So 220, because we are writing it in millimeters. Okay. Hmm. So this is in millimeters. This is in millimeters. So this is the diameter. So this is how I'll calibrate it. You see. Don't get confused. This is just calibration. So from here, let me also calibrate this one well, so that at the end of the day, yes, as you are seeing over here, that is it. As simple as that. Okay. So from here, what do we do next? We just put down the formula for our stress. I even feel like we can calculate for the area to avoid any form of issue. Okay. So we know that the area is equal to pi d squared over 4. So our area now is equal to pi d squared over 4. So let me say pi d squared over 4. Pi d squared over 4, which we now know is 3.142. So 3.142. Okay. So that is 3.142 all over 4. Okay. Times, in this case, our D becomes 50. So this is 50 millimeters. 50 millimeters. We square it. So at the end of the day, quickly punch this, quickly punch this, quickly punch this together on the calculator and let me know. What are you going to get after punching this? What are you going to get after punching this? 19.6375. That is what I'm getting. Yes. Patricia had the answer, and that was very wonderful. So finally, we now know our area 2, and that is our A3. Our A3 now is equal to what? 1963.75. Okay, that is millimeter hot squared. I want to make some one or two things clear before we proceed. Okay. This A2 is not just any A, but it is actually the A2. You see. Uh-huh. This one too is not just any A, but actually A2. Uh-huh. As you are seeing, as simple as that. This one is also not just any A, but also what? The A1. Uh-huh. As we calculated for initially, just to make certain things clear to avoid confusing anyone. Okay, this one was also A1. Uh-huh. So let's continue from where we are. After we had 19.6375 millimeters square, we can just calculate for our stress. And that is finally we say that our stress 3, our stress in section 3 is equal to the load P. That is equal for all over the A3, but not just any 3. You see. Uh-huh. So now we can say that the P, which is 35,000 for all, we maintain it. 35,000 Newton. 35,000 Newton all over 1963.75 millimeters squared. Okay. So quickly, let's all punch this together. 30, that is 35,000 all over 1963.75. So I had my answer. I'm hiding it. Let me see. What answer are you also getting? Okay, Daniel also had the answer. He had 17.8230 Newton per millimeter squared. Yes, exactly. So finally, we know that what, therefore, our A3 is equal to 17.8230 Newton per millimeter squared. Newton per millimeter squared. Exactly. So we are done solving the question A. You see, we are done solving the I. Since we are done solving I, it means that we also have to go and solve the II. You see, we also have to go and solve the I. So let's quickly go to solve II. Let's quickly go to solve II. Even before that, let's correct our calibrations. So this is I, and this becomes the II. So let's proceed. Let's proceed. Let's proceed. Let's proceed. So from here, we are going to now be calculating for the total extension of the bar. We are now going to be calculating for the total extension of the bar. We are now going to be calculating for the total extension for of the bar. So the total extension is also denoted as this, as we are seeing over here. That is the total extension. That is the formula for the total extension of the bar. Okay. From whatever we learned previously, we are going to apply that same idea over here. So let me denote here as II. Before that, I want to also correct something over here. So this becomes our II, and this is the total extension of the bar. So let me write over here, total extension of the bar. So this becomes our total change in length. I can even write total change in length, don't get confused, but let me maintain the grammar. So this is the total extension of the bar. Total extension of the bar. Total extension of the bar. Of the bar. Total extension of the bar. So I'll just underline it nicely and then we proceed. So the total extension of the bar, as we all said initially, we can denote it like this. If you see this, That is the total extension of the bar. Okay. Since we have three sections, we can say that what? The total extension of the bar is equal to what? The change in length in what? Section 1 plus the change in length in section 2. That is the change in length in section 2. Okay. Plus the change in length in section 3. Plus the change in length in section 3. You see, exactly. So after we have gotten here, what can we do next? What can we do next? It's just a matter of substitution and life become much more easier. But ask yourself that which kind of change in length formula are we going to use over here? Which kind of change in length formula are we going to be using over here? But before that, let's discover something. So let me just do this. It means that we want to discover something quick, before we proceed to solve our work. Okay. We know that the change in length, we know that change in length has so many formulas. Okay. But which one are we supposed to adopt in this case? First of all, we know that the strain is equal to what? Change in length. Okay. Over the original length. Now we know the original length. We don't know the strain. Can this formula work? No, this formula cannot work. Okay. So it means that we have to look for a different formula. Okay. Okay. Also, we know that our E is equal to what? Stress over strain. Stress over what? Strain. But also we know that what? The stress over strain can also be expressed in a more simple form. Okay. So this over here that we are seeing over here can also be what? Expressed in this form as you are seeing over here. So I'm going to just put that down. And this is the same as what? E is equal to what? The stress, it can be written as this: load over what? Area. Load over the area. Okay. Divided by the strain. That is what? Change in length over original length. You see, good. Change in length over the original length. Now, this that you are seeing over here, if at the end of the day I want to get rid of the division sign, then it means that this can also be written as what? E is equal to what? E is equal to what? P over A. P over A is equal to what? P over A times, you reciprocate this one. Okay. Now it's going to be L over what? The change in length. So finally, you see where we have gotten to. We are still trying to derive a formula. Finally, if I want to make that the subject, what are you going to realize? If I want to make this change in length the subject, what can we do over here? Okay, if you want to make the change in length the subject, this is it. Realize that we now have what? E is equal to PL all over A multiplying what? The change in length. Okay. A multiplying the change in length. So finally, what are we going to say? We want to make the change in length the subject. Okay, I told you that this guy over here is over 1, but we don't write it. Because of that, we are going to do cross multiplication over here. Okay, so this E that you are seeing is going to multiply everything you are seeing over here. So we are going to write E times what? Now, A multiplying change in length. A multiplying change in length. Also, please don't get confused. Also, our equal to sign is going to come. Okay, and we can say that our PL load times this is now also going to multiply what? The one you are seeing over there. Finally, this is going to give us something known as what? Let me divide here because I have more to still write. So this is now going to become, let me change color. So this is now going to become what? E hot dot A dot change in length is equal to what? PL. Okay. So what do you think? If this has now become like and I have to make one the subject to get the friend. Then at the end of the day, if I make my change in length the subject, what do you think is going to happen? I divide both sides by whatever you are seeing. Okay. So if I divide both sides by E over A, then you realize that finally, my change in length is now going to become change in length is now going to be equal to what? Okay, let me do it at the other side for you to see. So this is what we are having. Okay. This is what we are having. So at the end of the day, if we're having E multiplying what? The area, okay, times the change in length, which is equal to PL, which is equal to the PL. Then at the end of the day, if I divide here by what? EA. And also, I come and divide here by EA. Then you realize that at the end of the day, if we cancel both sides, we are just going to be left with something very unique. Okay, so this one will take care of this one. So finally, you realize that our change in length is now going to be equal to what? PL over what? E multiplying the A. So that is what it means. So finally, this is the formula we are going to use to solve our work. Okay, so wherever you see the change in length, I'm just going to put PL over A. Once I solve this one here today, I may not solve it anywhere again. Okay, so let's maintain it. So from wherever we have written, we are going to still maintain it, and now we continue to solve our work. Okay, so initially we wrote what? We said our change in length. That is our total change in length. Okay. Initially, we said our total change in length is equal to what? Change in length of section 1. Okay. Plus the change in length of section 2. Plus the change in length of section 2. Plus now the change in length of section 3. You see? So if I want to now, I'm saying I want to now get a total. Now from substitution, I'm just going to substitute everything into my formula. So look at what I'm going to do. So I'm still looking for my total change in length. Okay. But I want to solve all at once. I could calculate for it individually, and later I'll come and add it. But if you still want to do all together, to it is accepted. Okay. So if I'm going to now bring 3 boxes and close it nicely as you are seeing. So this is it over here. Okay. Plus another one as you are seeing. You see exactly as you are seeing over here too. The same thing. The same thing. You see. Okay. So now this one is not, the first one is going to become what? P1 L1 over E1 A1. But you see that in this case they all have the same. Okay, let's put this down in this before we later come to that. So from here, anyway, I'm going to write here. I'm going to write what? PL over A. Okay, PL over what? EA over EA. Okay, but since I'm talking about section 1, so at the end of the day, let me put 1 beside them. Dot means they are multiplying. So this is 1, this is 1. So here, what am I going to write? I'm going to write P2 multiplying what? L2. Okay. All over the E2 multiplying what? All over the E2 multiplying the A2. And finally, we have what? P3. P3 multiplying the what? L3. All over E3 multiplying the what? A3. Okay, so from here, since the material are all being acted upon by the same load, P, and also they all have the same E. Look at the question. They all have the same load and they all have the same elasticity. So at the end of the day, we can substitute the load and the elasticity out to solve the question. So let's substitute the load and the elasticity out. So finally, if I want to substitute the load and the elasticity out, this is what I'm going to get. So finally, my total change in length. I'm just going to substitute the elasticity and the E out since they are all the same. So I'm going to bring P out. I'm also going to bring the hot E out because they are the same for all. Okay. Uh-huh. So now I'm going to open a bracket which will be common to all of them. And now what am I going to say? The first one is going to be hot. It's just going to be L over A, you see. So I'm going to say L1 over A1 plus this one is now also going to be L2 over A2 plus here is going to be L3 over A3. Okay, please, any question before we proceed? Anyone having any question to ask before we proceed after from this place? Any question before we proceed? All right. So if no question, then from here it's just a matter of substitution. Okay. So let's do our substitution. Let's do our substitution. Let's do our substitution. That is our total change in length can now be what? We know here to be 35,000. So let's put it down 35,000 all over what? The elasticity. And the elasticity was 2.1 times 10 exponent 5. So 2.1 times 10 exponent 5. 2.1 times 10 exponent 5. Okay. Uh-huh. Then we can now bring our multiplication sign over here. And that is good. Good. So the first length, let's go back to our page one. This one was 200, the other one was 250. So the first one was 200. And the area we had for the section one was what? 314.2. Okay. 314.2. So over here we had 314.2, 314.2. And our length, what was the answer for our length? Our length, we had 200. So we write it over there. 200. This one, the length was 250. So we put a 250 over here. And then the area was 706.95. 706.95 plus the last one. And the last one, the length was given as 220. So 220 all over our last area we calculated for. So look at the section 3, 1963.75. So let's put it over there, 1963.75. 1963.75.